Hi, myself Prabharan from Physics Department, Hindustan College of Engineering and Technology. Today we are going to discuss about magnetic materials and its fundamentals. Let me start the session with the Albert Einstein quotes. Learn from yesterday, live for today, hope for tomorrow. If you can't explain it simply, you don't understand it well enough. Let me start the session. This is lecture 2 from magnetic materials. Today we are going to discuss about the classification of magnetic materials, diamagnetic materials, paramagnetic materials and ferromagnetism. Classification of magnetic materials. Materials which lack permanent dipoles are called diamagnetic. If the permanent dipoles do not interact among themselves, the material is paramagnetic. If the interaction among permanent dipole is strong, such that all the dipoles line up in parallel, the material is ferromagnetic. If the permanent dipoles line up in anti-parallel direction, the material is antiferromagnetic and ferrimagnetic. Materials not having permanent magnetic moment, that materials are called as diamagnetic materials. If the materials does not have any permanent magnetic moment, then we are calling that as a diamagnetic material. If the materials have permanent magnetic moment, then we can call that as a paramagnetic, ferromagnetic, antiferromagnetic or ferrimagnetic. Please understand, if the materials not having any permanent magnetic moment, it is diamagnetic. If the materials having permanent magnetic moment, they are para, ferro, antiferro and ferri. But depends upon the magnetic interaction between any two dipoles, we are classifying para, ferro, antiferro and ferrimagnetism. If there is no interaction between dipoles, then we are calling that as a paramagnetism. Dipoles line up in parallel, we are calling that as a ferromagnetism. If the dipoles line up in anti-parallel, we are calling that as a antiferromagnetism or ferrimagnetism. First we will discuss diamagnetic material. The material initially does not have any permanent dipole moments. However, when it is placed in an external magnetic field, the dipole's moments will be induced in it. Please look at the diagram. Please look at the diagram. When H is equal to 0, when the magnetic field is 0, there is no magnetic moment. However, when a magnetic field is applied, H is equal to H naught. Now what happens there means, the magnetic field will be induced in it, but the induced magnetic field will be acting in the direction opposite to the direction of applied magnetic field, so that the magnetic dipole moments opposes the applied magnetic field strength. So from the bottom diagram you can clearly observe, if it is a normal material, the magnetic lines of force will penetrate into the material. Suppose if it is a diamagnetic material, the magnetic lines of force are repelled by the diamagnetic material, so that the magnetic flux density inside the material B is equal to 0. Some of the properties of diamagnetic material. They repel the magnetic lines of force. Susceptibility is negative and is independent of temperature. Even if you increase the temperature or decrease the temperature, it will not affect the susceptibility of a material. Third one, the value of permeability is less than 1. Fourth one, no permanent dipole moments in the absence of magnetic field. Fifth one, when the temperature is lesser than critical temperature, diamagnetic becomes normal material. Example for diamagnetic materials are gold, germanium, silver, lead, copper, organic materials, etc. Now let me go for paramagnetism. Even in the absence of external magnetic field, the material possesses some amount of magnetic induction or magnetic dipole moments, but they are randomly oriented. So the net magnetization of the material is 0. However, when it is placed in an external magnetic field, the magnetic dipole moments tends to align themselves nearly parallel to the applied direction of magnetic field, so that the material will be magnetized to certain extent. This is called paramagnetism. Each atom possesses a permanent magnetic moment. When H is equal to 0, all the magnetic moments are randomly oriented so that the magnetization is 0. When a magnetic field H naught is applied, the magnetic moments tends to orient themselves in the direction of field, resulting in positive susceptibility. When an external magnetic field is applied, the magnetic dipoles tend to align themselves in the direction of magnetic field and the materials become magnetized. This effect is known as paramagnetism. The paramagnetic susceptibility decreases with increase in temperature, so it is inversely proportional. Susceptibility varies inversely with the temperature. As the temperature increases, the susceptibility decreases. It is chi is equal to C by T. This equation is called Curie law of paramagnetism and C is constant called Curie constant. The magnetic susceptibility is positive and it is greatly depends on temperature. The magnetic lines of force passes parallel through the material. Since magnetic lines of force passes through the material, they possess permanent dipole moment which makes permeability greater than 1. Magnetic susceptibility is independent of applied magnetic field. They possess permanent dipole moment. When the temperature is lesser than Curie temperature, paramagnetic becomes diamagnetic. Example: copper sulfate, MnSO4, platinum, chromium, NiSO4, etc. Now let we discuss ferromagnetism. There are certain materials like iron, nickel, which have high degree of magnetization in spite of their randomized tendency of their thermal motion of atoms. These materials are called ferromagnetic and the phenomenon is called as ferromagnetism. It has a characteristic temperature called the ferromagnetic Curie temperature, theta suffix f. Since some magnetization is already existing in this material, all the magnetic lines of force passes through the material. The second property, they have permanent dipole moment, so they act as strong magnets. They exhibit magnetization even in the absence of external magnetic field. This property is called spontaneous magnetization. Fourth property, its susceptibility is positive and high. Also, it depends on temperature. So, chi is equal to C by T minus theta. This equation represents Curie law of ferromagnetism. Fifth property, when the temperature is greater than Curie temperature, ferromagnetic material becomes paramagnetic material. Permeability is very much greater than 1. Seventh property, they exhibit magnetization even when the magnetizing field is removed. Hence, they exhibit magnetic hysteresis. Example for ferromagnetism is nickel, cobalt, iron, etc. I have shown the comparison of dia, para and ferromagnetism. First, I have shown the comparison of definition. So, diamagnetism means initially it does not have any dipole moment. When it is placed in a magnetic field, the dipole moment will be induced, but it opposes the applied field. Paramagnetism means initially there is a dipole moment, but it is randomly oriented. When it is placed in a magnetic field, it will allow the magnetic lines of force to pass through. Ferromagnetism means it will be strongly magnetized because it is having initially small amount of magnetic moment. That is called spontaneous magnetization. The second comparison is temperature dependence. Diamagnetic material independent of temperature, but paramagnetic and ferromagnetic depends on temperature. It is inversely proportional. The third property, behavior of material in the presence of external magnetic field. The diamagnetic repels, paramagnetic attracts, Ferromagnetic strongly attracts the applied magnetic field strength or magnetic lines of force. The fourth comparison is movement of magnetic flux lines. The magnetic lines of force are repelled. Here the magnetic lines of force are strongly attracted. The magnetic in ferromagnetism, the magnetic lines of force are very much strongly attracted towards the applied magnet. The fifth property is or comparison is spin alignment. There is no spin alignment for diamagnetism. For paramagnetism, all spins are oriented, but it is randomly oriented. In ferromagnetism, it will be oriented in one particular direction. The sixth comparison is origin. Arises from the Lamar precision of electronic orbits in the presence of applied magnetic field. Arises from the paramagnetism means arises from the magnetic moments originating along the external magnetic field direction, and magnetic moments orientation is largely determined by temperature and magnetic field. Ferromagnetism, it arises from the spontaneous magnetization. The seventh comparison is magnetic phase transition. When the temperature is less than critical temperature, the diamagnetic suddenly disappears. For paramagnetism, when the temperature less than Curie temperature, it is converted to diamagnetic. For ferromagnetism, when the temperature is greater than its Curie temperature, it converted to paramagnetism. Permeability is very less for diamagnetism. It is very high. It is simply high for paramagnetism, very high for ferromagnetism. The ninth comparison, susceptibility. It is negative for diamagnetism. It is positive and small for paramagnetism. It is positive and large for ferromagnetism. As we discussed the example, diamagnetism, hydrogen, bismuth, gold, antimony, germanium, niobium. For paramagnetism, aluminium, platinum, chromium. For ferromagnetism, iron, nickel, cobalt, steel, etc. Thank you all.